Right, now number 8. Okay, number 8. Let's see. Okay, number 8 is yet another quadratic equation. We need to look for the set of values of x for which y is greater than 13. Okay. Now, as usual, you can use graphical methods, or you can depend solely on algebra and a bit of graph to help you to verify your solutions to that inequality. Okay, so in this case, given y is greater than 13, so the y is 2x squared minus 6x plus a 5 greater than 13 there. All right, now as usual, we're going to arrange that so that we have standard quadratic equations. I think that is 8 more than 0 there. So, yeah, correct. So from here we have x squared 3x 4 there. So x minus a 4 plus a 1 there greater than 0. Okay. So from here, again, by rules, you can memorize this without using the graph. We know specifically x is less than negative 1. Oops, shouldn't use the comma there. Equals to negative 1. Or x is greater than 4. By graph, just for checking, if you like to check whether your answer is correct, you might want to sketch out the graph in this case. Okay, sketch out the graph for this one. It's not this one here, right? So let's sketch out the graph for this. It passed through a 4 and a negative 1. So somewhere here, a 4, and then recognize whether it's concave or convex. So in this case, it's a convex curve. Yep. And then it passed through somewhere like negative 4. Okay, so we are asking which part of the graph that is actually above the x-axis. So it's quite obvious. It's this section, anything less than negative 1, and then of course you have another section whereby x is greater than 4 here. Right, so that confirms our solutions. Okay, number 2. Find the value of the constant k for which the line is a tangent. Alright, now you can see the line is a tangent, so we apply the same strategy. We will let 2x plus k equate that with the quadratic equations. Quadratic equation of the curve plus 5 here. So rearrange. We have oops, hold on. We have 2x minus 8x there plus 5 minus k is equal to 0. Because it is tangent, therefore discriminant b squared minus 4ac must be equal to 0. Again, for safety precaution, we write down a is 2, b is negative 8, c is 5 minus k here. Always check. So negative 8 square, my a is 2, my c is 5 minus k here is equal to 0. So if you actually simplify every thing here, that is actually 8 minus 5k. I do it differently sometimes. So that is actually a 3 plus a k. So k is equal to negative 3. Right. Okay, just let me check it visually very quickly. That will be a 8, a 3, and then a k. Yep. So the k is equal to negative 3. Of course, you can verify it more thoroughly to ensure the k is correct. Right? Here, I'm just doing a rough mental mapping to verify my k. Right. So I hope if you like, do go ahead. check it thoroughly. Okay, just let me check if there's an extra question here. Okay, no, done. And now I'm going to move on to just let me check. Question 9. Yeah. All right, question 9. All right, question 9 is a long one. Okay, question 9, number 1. Okay, question 9, number 1. Find the range for fx. Okay, now I'm going to use the non property of signs. Use the property of sine. Okay, where we know that sine x is lying between 1 and -1, and then in this case sine 2x is also lying between 1 and -1. So I'm going to use this property to find the range easily here. Okay, now again marking here, so this one is maximum value for this sine, and this is the minimum value. I hope that you still remember the technique that we're going to use over here. Now we're going to find minimum value of fx. So we're going to find minimum value of fx. Minimum value for fx is 5 minus 2 bracket here. In order for these whole expressions to be minimum, therefore this value here must be maximum from here. So which one is maximum? That is a 1, so I'm going to put a 1 here. Okay, from here I'll get myself a 3. Next, I'm going to get the maximum value of fx. Maximum value for fx. So maximum value for fx. In order for me to get these expressions to be maximum, I need to make sure that this section here must be minimum. Okay, which one is minimum? -1. So I'm going to put that in. I'll get it in. Therefore, range of fx is lying between a 3 and 8. Lying between 3 and 8 there. Okay. So I hope that is clear here. Right. Now that is by using the non-properties of sine function. Okay, right. Now, if I were to use a graph, okay, I might want to show you. If I'm going to use the graph just for checking purpose here. Okay. As usual, I'm going to sketch the axis first. So I have something here. Okay, just let me mark this properly here. X are still in radian. Okay. This is a y equal to fx here. This is 0, and then that is between 0 and pi. Okay, 0 and pi. So I might want to divide this into half a pi, and then this one will give me a pi there. Okay. Okay. Pi over 2 and a pi here. Okay. All I need to do is just try out. Now, starting from x equal to 0. When x equal to 0, I would get myself. Hold on. I'll get myself a 5 for sure. It's a 5. So okay, a 5. So I'll get myself a 5. Just let me mark it properly here. This is 3, 5, 7. It's not a good scale to use here. I purposely use this just because I know that the range is between a 3 and a 7. Is it 3 and 7? Just now it's 3 and then a 7. Yeah, I think it's 3 and 7. Yep. 3 and 7 and 3 and 8. Yeah. Okay, so x equals 0. When x equals 0, I have a point here of 5. So when x is equal to pi over 2, so if you try pi over 2, that is also a sorry, that is not. Just let me correct that. So when x equal to pi over 2, that is also a 5. Oh, now life becomes very interesting. Okay, and then when it's pi, that is also a 5. OMG, that is a straight line. But I do recognize that the sine graph is a graph that has a certain period. It's a periodic function, so it cannot be a straight line, though. So I'll keep on going since I can't actually figure out the rest. So I might want to expand my scale a bit. So instead of having 90 degree, I might want to further divide that into here, and then that will be like 3 pi over 4 here. Alright, let's give it a try. If it is pi over 4, then and then that will be a 3. Okay, now I'm getting somewhere. Okay, hold on. Better use different marking here. Now I'm getting somewhere. And then I can also test out when it's 3 pi over 4 here. So that will be a 90, 270 degree, and then that would actually yield a 7. You can check with your calculator. So from here, it's pretty obvious that the graph. Okay, I might use a different color for this. Okay, hold on, just let me finish drawing that. Okay, the last one is not very accurate, doesn't matter, but roughly it looks something like this. And now you can see that the graph is having a range from 3 to 7. So the range of fx is from 3 to 7. Okay, so this is also another way to verify the range using a graph. Okay, so that is number 1. I hope that is clear. Again, if there's any error in the presentation, do drop a comment. All right, thank you very much. Okay, so let me clean this up. We're gonna move. Okay, sketching. Okay, hold on. Just let me. I accidentally erase everything, so just let me put it back. Okay. So the sketching. The second one is the sketching of this graph. Sketch the graph y equal to fx. So I have already sketched the graph for y equal to fx. Now, what I did here is a little bit different from before. I'm actually sketching it out one shot without doing any transformation. So if you want to go into the detail of how the graph is being produced through the help of transformations, by all means, give it a try. Okay, so that's number 2. We are done. Now we need to solve the equation fx equal to a 6. Fx equal to a 6 basically means we are trying to find the intersection between this straight line y equal to 6, y equal to 6 here, and the sine graph fx. So as we can see here, there are 2 solutions, or 2 roots, or 2 solutions, or 2 intersection points. These are the 2 solutions that we expect to get. We need to leave the answer in terms of pi there. So how am I going to obtain this and this, both of these solutions? Or sometimes this will be clear. It's also called roots, yeah, or intersection. Okay, so just let me clear this part. I'm going to answer this part here. Number 3. Okay, solve fx equal to 6. My fx is given by phi 2 sine 2x equal to 6. And then from here it's quite obvious that sine 2x is actually equal to negative 0.5. Negative 0.5. Okay, negative 0.5. Okay, negative 0.5 is would actually give us 2x in this case. If you press your calculator on this here, it will be just let me check through. Pi over 6. So pi over 6 so plus a pi, that will be a 7 pi over 6 there. If you press your calculator, it's 7 pi over 6 on this. And then the second answer for this will be, hold on, let me see, 11 pi over 6. And then from here we can verify our solutions x as this or this. Right. So there are two solutions here. There are two solutions. These two solutions are still within that domain there. So therefore we can accept both of these as the solution. Right. So I hope that this is clear. If you're not very sure of this solution, you can always refer to the solutions to trigonometry ratio. Revisit that sections one more time. Right. Okay, that is clear. So we are done with number 3 now. Okay, just let me check the rest of the questions there. Okay, state the largest value of k for which g has an inverse. Okay, g has an inverse. Okay, that's good. That's good. Since we are referring to the same graph, I will leave this graph here. Okay, just let me erase the sections that we don't need. Okay, that is number 3. We are looking at number 4. It's the same function. It's the same function here. So let me clean this up. We don't need this at this point. Okay, and then since they are using gx, I'm going to change this to number 4 now. We will relabel this. Anyway, fx and gx is more or less the same, other than the domain itself. And then we don't really need this piece of function at this point, so I will erase all this. Okay, it's pretty challenging to erase this. Okay, never mind, just let me clean this up. Okay, so that's it. This is our function. Okay, these are our functions here. Okay, there you go. That's our function. Gx. This is our function Gx. But this function Gx is not one-to-one. So therefore, that's the reason why we need to restrict the domain here. And then they have already set the starting point for the restriction. X is greater than 0, meaning that it starts from here. Is the starting point. And then we need to go until the point where an inverse can exist, where it is still a one-to-one function. So as you can see from here visually, the only sections where it can still be considered as one-to-one is up to pi over 4. So up to here. Therefore, based on the graph, we should restrict, just let me to have, I would say, to have an inverse for gx. we must restrict the domain to, okay, must restrict the domain in this case to x is greater than 0, less than pi over 4, based on this diagram. And then to answer this, find the largest value of k. So I would say that largest, in this range here, the largest value of k is pi over 4. For g, for inverse gx to exist, or you can say that for gx to have an inverse. Yeah. So we are done with that. And then finally, we're going to find the inverse functions. Okay, so inverse function shouldn't be a problem here. I will keep the graph here. Sometimes it's good for us to finalize the domain sometimes. Okay, so the last sections here, number 5 here. Okay, so as usual, we are going to let y equal to 5 minus 2 sine 2x. Okay, so 2 sine 2x is equal to 5 minus y, and then sine 2x equal to 5 minus divided by 2. 2x is inverse sine 5 minus y, and then therefore we can conclude that the inverse function is actually these two. You have to move it over, of course. That is inverse sine of 5 minus x 2. Now, of course, in this case, we should know the domain. The domain for this must be greater than or equal to 3, or anything less than a 5, because the domain, the range for the gx become the domain for the inverses. Right. So I hope that is clear to everyone. Okay, so I'm going to move on to 10. Alright, we are almost there. Okay, hold on, just let me check one more time. Okay, done. So 10, we are done. We're going to go to 10 now. Alright, 10. Okay, I forgot to erase this. Alright, number 10. Okay, number 10 is just another quadratic equations, and then relevance to completing the square. So just let me finish this quickly. Number 1, we need to express this quadratic equation in the form of completing the square, but with a little bit a change to the way we express completing the square form in this case. Right? Okay, let's give it a try, see whether we can achieve that. Alright, now as usual, we are going to factorize that. Now I'm going to follow the original way, because that's how you learn about this. Unless you want to modify your algebraic approach, by all means you can do so if you have discovered another way to sort of manipulate your algebra, right? So I'm going to do it a bit old-fashioned way in this case. So I'm going to remove off my 9. Okay, like this. Okay, so I'm going to remove off my 9 like this, and then as usual I'm going to follow the rules, having coefficient x squared to be 1, and then that would actually yield 6 over 9 here, just to make it easier for you to recognize what is going on. Of course 6 over 9 you can simplify it to 2 or 3 here. Okay, so I'm going to do that. Alright, after that we can do complete the square for this. That is 1/3 minus 1, 9 plus 6, and then from there we're going to expand that. Oh, sorry, I forgot my square here. I'm going to expand that, and then that will become a 5. So just let me roughly expand that, and then to see whether I'm getting everything correct. Negative 6, 1 over 9, negative 1, sorry, positive 1 plus a 5, yeah. So that is the correct format, right? This is the usual completing the square form. It's easier to use this form rather than the form that they requested here, because here we can get the vertex, the minimum point easily. Okay, but anyway, let's try to express that in the form that they want. To do so, this 9 I can write down 3 to the power 2. Okay, now you can see that by using index rule, because the index is the same, therefore I can multiply my base. Therefore I can join the base together. So it's also a bit of revisit on index rule. From here I'm going to expand this, so that will be minus 1. I hope I got that correct. Okay, plus a 5. And now if you compare this with this, yes, we managed to find or to discover this format where A is equal to 3, B is equal to negative 1, and C is equal to 5. Alright, so that's how we would usually carry this out. Of course, there is many other ways we can manipulate your algebra so that you can get the completing the square form to be in this format, right? Or you can stick to the more traditional way, like what I did, right? Do send in suggestion if you have any other methods that you want me to present, right? Okay. Now next, number 2. Okay, number 2. Right, number 2, the function f is defined as this, which is exactly the same as this. The only difference is x is greater than p, where p is constant. Now the smallest value of p for which f is a one-to-one function. Now as usual, I'm going to rewrite f and then I know that this can be written as, oh, so I'm going to use the previous result that I have. This can be written as 3x minus 1 square plus a 5. Yeah, that's how it looked like. Let me see whether that's yeah, correct. Okay. So in the completing the square form in this case, we know that the least value of fx is 5 when x is equal to 1/3. Okay, therefore therefore we need to restrict the domain. We need to restrict the domain to this one, to x is greater than p. X is greater than p. I accidentally copied that. X is greater than 1/3 for fx to have an inverse. For fx to have an inverse. Okay, hold on, just let me clean that up. For fx to have an inverse. Yeah. So the smallest value of p is 1/3. Okay, I hope that is clear. Okay, number 2, we need to obtain the expression for the inverse. Okay, obtain the expression for the inverse. Now let me clean up the rest first. Okay, so this is done. Okay, I'm gonna write that down. This is number 3. I still need this function in its completing the square form. It's easier for me to recognize in this case. I know that I need to restrict this to 1/3. Okay, but once I restrict this to 1/3, the range for fx, the range for fx would be, in this case, it would be greater than, in this case it will be greater than 5. So the range will be greater than 5. Okay, so the range is greater than 5. We will need this in a while. Okay, let me work out the inverse functions. Let y equal to 3x minus 1 square plus a 5. 3x minus 1 is equal to y minus 5 plus or minus, just like to revisit this one more time, and then therefore my x is equal to 1/3 of 1 plus or minus y minus 5 here. Okay, so that come back to the questions whether I should adopt a positive or a negative here. Since the x are all greater than positive number here, most probably I'm going to adopt the positive one. So I'm going to erase this. So I'm going to erase that, will be my final one. Okay, maybe at this point you can write it like this, but later on the inverse function for this we will write as 1/3 1 plus x minus 5 square root. Right. And in this case we can say that the domain must be greater than 5. Domain must be greater than 5. So that is the domain for this. Okay. So that's number 3. Lastly, state the set of values of Q for which the equation has no solution. No solutions mean no real roots. Okay, so just let me clean that up. Okay, so that is last one. Fx equal to Q, and then yeah, maybe it is best at this point of time we try to use back its original function. We will have 9x minus 6x plus 6 minus q after I move everything over. Okay. And then recognize that a is 9, b is -6, c is 6 minus q. And then knowing that no solutions means my discriminant must be less than 0. Then I'm going to put in here minus of 4, a, and then c less than 0. Okay. And then by simplifications, you have less than 0 there. And then we have here -5 plus a q less than 0. And then therefore q must be greater than sorry, hold on. Q must be less than, I think I did this, write it down wrongly, less than. Okay, just let me check it. Yeah, so q must be less than sets of value. So q are all real numbers such that q is less than a 5. So q is a set of all real numbers such as q is less than 5. Alright, so I hope that is clear. Alright, so if you are done, if you are ready, let's move on to 11 now. Just let me double check if there's any extra sections there in case I accidentally forgot. Okay, no. Okay, 11. question 11. Right. Number 1. A curve is given by that expression and a line, straight line. Show that the coordinates of the points or intersections of the line and the curve are given by the equations here. Right. Now, since they are intersecting each other, therefore, we can state that x squared minus this must be equal to this because they are intersecting. Okay. And then if we rearrange that, we will have a 4x plus 3 minus a equal to 0. So since they are intersecting, the x coordinate of the point intersection of the line and the is given by this. Yeah, so this has been shown. Okay. Number 2, for the case where the line intersect the curve at 2 points, it is given that x coordinate of one of the points of intersection is -1. Okay, so one of the solution is stated that it is given that the x coordinate of one of the point or intersection is -1. Yep, is -1. So find the x coordinate of the other point of intersection. Okay, now since x is equal to -1, since x equal to -1 is one of the solution. Therefore, this solution must satisfy this equation here. So we can substitute this x equal to -1 into here. Therefore, we have -1 square minus 4 -1 plus 3 minus a equal to 0. Right? So from here we have, hold on, just let me clean this up. Okay, so we have here a 5 plus 3 minus a equal to 0 there. So therefore a is equal to 8. So a is equal to 8, but that is not what we are trying to find here. What we are trying to find is, since the a is equal to 8, therefore this equation here can be rewritten as x squared minus 4x -5 equal to 0. And then solving this would yield x minus 5, x plus 1. Therefore, x is equal to -1 of 5. Since one of the x coordinate is -1, the other x coordinate must be a 5 there. So that's done. Alright, so I hope that's clear. Number 3. One, two, 3. For the case where the line is a tangent to the curve at the point P, find the value of A and the coordinate P. Okay, so if they are tangent to each other, therefore we're going to refer to this one more time. If they are tangent, so it means that discriminant must be equal to 0. Again, as a good practice, even though we need to write this a few hundred times, it's always good to remind ourselves, I need to rewrite it again. Okay, but bear in mind this A is the A that we're using here. It's not this A, so I better put a marker there just to remind myself. Now in this case it will be 4 squared minus 4a. C is 3 minus a equal to 0 there. So there's a 5 minus 3a equal to 0. Okay, so that will be a equal to -1 there. Okay, so a is equal to -1. We have indirectly found the value for a. Now we need to identify the coordinate of intersection. Once we found this to be -1, then we can rewrite this as x squared minus 4x plus a 4. And then in this case, it's very obvious if you factorize that. X is equal to 2 there. Right. So the coordinate for P, when x is equal to 2, then the y must be equal to a 5. Let me check whether I got that correct. 6, a 5. Yes, correct. Therefore, I can conclude that coordinate P has coordinates of 2, 5. Alright, so I hope that is clear. Alright, so we're almost there. So just bear with me on this. Just let me see any extra questions anymore. Alright, I think we are at, we are not done yet. This is just question 12. Okay, we still have some more to go. Just let me check. 13, 14. Okay, this time there's an extra 2. So let's start with 12. Okay, 12. Okay, 12 is right now another quadratic equation. I'll find the set of values of k for which the whole of the curve lies above. This is another different conditions given to us. It says that the curve is lying above the x-axis. Given y is equal to x squared minus 6x plus k. Since they want the curve to lie above the x-axis, so this curve y is above x-axis. So lie above the x-axis, I would make assumptions the y is greater than 0. The y is greater than 0, but it's not discriminant greater than 0. So from here, we have greater than 0. So you need to find the set of values of k for which the whole of the curve is above the x-axis. Above the x-axis. The whole thing is above the x-axis. Right now, you might be wondering whether we can use discriminant and so on. Okay, that is good thoughts. We're going to verify that in a while, but I'm going to show you how I'm going to do it based on my perspective in this case. Right? So I would revisit my completing the square methods again. Okay, so that would actually give me x squared. There's negative 9 plus k minus 9 greater than 0. Right? I know that x from this expression here, I know that x minus 3 squared must be greater than or equal to 0. That depends on what value of x that I'm working with. Must be greater than. Which means the smallest value I will get is 0. The rest must be greater than 0. Okay. Now, because this is a positive number, it's always a positive number. How am I going to ensure that this whole thing is greater than 0? The only way I can ensure that is I need to make sure k minus 9 must be greater than 0. Must be greater than 0. Therefore, k must be greater than 9. K must be greater than 9. This is solving this question using completing the square form. So this is the solution. Okay. How can I solve that using discriminant then? Yeah, so you might be wondering. Okay, I'm going to rewrite that here. Can I solve it using discriminant? Yeah. Can I solve it using discriminant? That's the key question here. So just let me rewrite this inequality. Let's try to understand it more in this case before we even apply b squared minus 4ac. Now they are saying that this graph here above the x-axis. So you can mentally sort of understand this, assuming that there's a graph x squared minus 6x plus k. Alright, now how are we going to ensure that this graph is actually above? How do you ensure that this graph is actually above the x-axis? The only way that this can be above the x-axis is when the discriminant is less than 0, because there is no real roots. So for that to be true, I will, as usual, I will write down a is equal to oops, this time what have I done? Okay, hold on. So my a is equal to 1. So my b is equal to -6, and then my c is equal to k. So from here, discriminant is less than 0. That means -6 squared minus 4ac must be less than 0. Okay, by solving this, I have 36 minus 4k less than 0. K must be more than 9. So you can see that both of these answers tally each other. So you can use either method. But knowing that discriminant can be used, you will have to have certain understanding of what are we looking at here. Okay, or if you're not sure, you can always depend on the completing the square methods. Okay, right. So we are clear on that. Okay, just let me clean this up. Let's go to second question. It's easier because we want to find the value of k for which this is a tangent to the graph. So all we need to do is number 2, let both of these to be equal to each other. It's just that the only catch is you have to rewrite this so that your y is the subject. So it's okay. We're going to rearrange this. Now this time our y is our y is a subject. So now we can assign both of these to form an equation. Right, rearrangement, that will be a 4x plus k minus 7 equal to 0. And then we know that it's a tangent. Again, a good habit, write down a is 1, b is -4, c is k minus 7 there. Discriminant must be equal to a 0 because it is a tangent. Now -4 square minus 4a c k minus 7 equal to a 0. This one will be a 4 minus a 4, 7 here. And then just let me see 11. So k is equal to 11. And then there you have it. There's a value of k for which this is the tangent to the curve. Okay, so I hope you guys are clear on this. All right. Okay, let's move on to the next one. Just let me check if there's any. Okay, no. So now is question 13. All right, question 13. All right, yet another quadratic equation. Okay, so many quadratic equations. I think at the end, you will get a bit tired solving quadratic equations. So if you are tired solving quadratic equations, I can give you some higher dimension functions to work with. If you are interested, drop me a comment. Okay, right. Now, first question, we're going to express this in the form of the completing the square form. We are given a concave curve. Okay, so I just need to follow the same ruling here. Okay, just number 1, express this 7 minus 2x squared minus 12x. Okay, I will follow the usual way to do this to avoid any unnecessary error here. Okay, so 12x, I'll rearrange this, and then factorization. When you factorize, have to be a bit careful because there's a lot of negativity. Yeah, correct. So be very mindful with these conditions that we are having. Just try to mentally expand that. Do you get the same one? Yes, I do. Therefore, I can proceed on. Square minus a 9 plus a 7 there, and then that will be like 25 if I simplify everything. Okay, so let me see, 1825. Right, now that's what we have. Again, try to check one more time. So there's negative 2x, 6, negative 12x, a 9, negative 18, negative 18, that would be a 7. Yes, okay, so that is correct. And then finally, all you need to do is just write down a is 25. Based on this, we have a 2, and then the b is a 3. And then we are done, right? Number 2, set the coordinate of the stationary point on the curve. So the stationary point, to get the stationary point, all we need to do is to let x plus 3 equal to 0. That would yield x is equal to negative 3. Now when x is equal to negative 3, the y value is 25. Therefore, we can finalize the stationary point as negative 3, 25. Now, that will be our stationary point. Okay, 1 and 2. Alright, now the next one looks pretty similar to all the questions that we have done so far. So number 3, I just rewrite gx. I will rewrite the gx in the complete the square form one more round, which is x plus 3 squared in this case. Okay, but this time we have to restrict our domain so that we can have a one-to-one function in this case. How are we going to restrict our domain? We have to restrict, here I will not go through all the working again. So we're going to restrict x greater than negative 3. Therefore, smallest let me see whether I got that right. Yeah, the smallest value of k is negative 3 for g inverse to exist. That's the key. Right? And then finally, we need to obtain the inverse for this value of k. Now number 4, k is negative 3. Okay, we're going to find its inverse. As usual, we will let y equal to 25 minus 2x plus 3 squared. And then from here you have plus 3 squared equal to y minus again. Okay, just let me correct that. That is 25 minus a y. We will have x plus 3 equal to 25 minus a y divided by 2. Divided by 2 square root that. As usual, there's a plus or minus. Now in this case, I'll just finalize the answer here. We are interested to get the inverse function of this, which is negative 3. And then since the x is greater than, so I will choose a positive here as usual. So x over 2. Now, of course, as usual, I will write down the domain for this. Um, the domain for this will be x is anything less than or equal to 25. Yeah, anything less than 25, right? Or else this expression cannot be evaluated. Right? So I hope that is clear. Okay, if you're done, we're going to move on. Okay, right, where we are, just let me check any extra note. Okay, are we at the final question? Okay, we are. Phew, that's a lots of quadratic equations that we are handling today. I hope that all these are useful to you. Okay. Again, as usual, if you like this, do subscribe and then press the notification bell sign so that whenever I upload a new videos, you can get the notification. Right? Okay, let's work out this. All right, now another quadratic equation. So it's more simplified. Work out the completing the square form, and then hence or otherwise find the coordinate of stationary point. We can work this one out and straight away obtain its stationary point. For the sets of value of x for which find the sets of value of x for which y is greater than -20. Okay, let's start off with this. As usual, I will rewrite in this form, and then I will factorize this, and then after that I will work out the completing the square form in this case. Let me see, is 16, and then finally I can write that down as 16 minus x minus 4 square. So again, I'm going to check that mentally whether I'm getting the correct answer here. That is a 16 like this. Okay, then this is the completing the square form. The a is 16, the b is -4. Right, now please be very mindful how you are going to express the b. Okay, hence or otherwise determine the stationary point. Now to find the stationary point, we will let x minus 4 equal to 0. That leads us to 4. So when x is equal to 4, the y value is equal to 16. Therefore, stationary point is 416. Okay, that's 1 and 2. I'm going to erase all this. Okay. All right, now number 3. For y greater than -20, all we need to do is just assign this, which is greater than equal to -20, and then rearrange it again. So this one would be less than 0. Okay. And then factorize that again. Okay, I hope I factorize it correctly. Okay, and then from here, you can also use by a certain rule. If this is less than equal to, then you can say that your x must be lying between -2 and a 10. Of course, to verify your answer, it's always good to sketch out the graph for this. Right? Now the graph for this is what graph is this? We are looking at a convex graph, even though originally it was concave. Okay, but we are interested in this, not the original one. Okay, now there is a 10, -2, and then a 10, for instance. So we're going to draw this like we have something like this. Okay, right? Then yep. Okay, so this is our graph. We are interested to find out which part of the graph that is less than 0. Which part of the graph that is less than 0. So it's very obvious. This is the part of the graph that is below. So the x value must be lying between -2 and a 10 because they are using inclusion here. So we have to use inclusion here. Right? Okay, so I hope that is clear. Always verify with the graph, no matter what, just to be on the safe side. Okay. All right. Now the next one, before we move on, I'm going to erase all this part here. I will leave the graph there. We might need it in a while. Set the domain and the range for this. Since we restrict the domain, okay, we restrict the domain up to this point. Okay, now before that, let me clean up some of the unwanted. Okay. Now we know that the vertex is located somewhere at 4 here. No, the vertex is located somewhere at 4 here. So at x equal to 4, the y is equal to, okay, how do I know that the vertex is equal to 4? Most of the time the vertex is the same as the restricted domain. But the other easy way to find the vertex is actually take the midpoint between these two x-intercepts. So 10 plus -2 divided by 2, which yield a 4. That's how we know that the vertex is located at x equal to a 4 there, right? So if you substitute this into the y, you have 1632. So which yield 16 there, right? So from here we can work out the inverse for this. Okay, we will let y equal to it's completing the square form here. The completing the square form that we have worked out previously here, right? So I hope that you still remember the completing the square form. Just let me recall that for a while. If I recall this correctly, that would be hold on, x minus 4, 16 squared. 16, yeah, correct. So 16 minus x squared minus 2x plus x, yeah, correct. So let y equal to this. Therefore, you have x minus 4 equal to 16 minus y square root plus or minus. So x is equal to 4 plus or minus 16 minus y here. Now again, we need to check the x value that we have here is always greater than 4. So since it's greater than 4, okay, therefore we can conclude that the inverse function for gx is equal to 4 plus 16 minus x, knowing that the domain must be greater than or equal to 16. Hold on, is it greater than or equal to 16? Did I get the domain correct? Hold on. Did I get the domain correct? Something not right here. Just let me check one more time. The x should be. The range for this is, okay, just let me verify one more time. The range for the original function is, okay, so the range is, alright, did I draw the correct? Oh, alright, now I know why I got the wrong one, because the domain originally was less than 16, so I'm drawing the wrong graph here. I better redraw the correct one so that you don't refer to the wrong graph here. Okay, that's why the graph is very important here. The graph that we are looking at is the concave graph. Okay. It's the concave graph at the 0 and 8. We are trying to sketch this graph, not the other. I think I referred to the wrong one here. So the concave graph would look something like this. Yep. Okay. This is a 4 here. The highest point is 16 here. So the range for fx is anything less than 16. Therefore, the domain here must be anything less than 16. Anyway, if you make your logical thinking, it can't be anything more than 16 there. So there you have it. That's the answer for that. Okay. And then find expression in terms of x for the inverse. Okay, we have already found the inverse here. I can just mark down number 5. But I think there's one section I forgot to answer. I have answered the domain, but how about the range? The range for the inverse must be the same as the domain. So you can say that the range, so the range is G inverse must be greater than 4. Okay. Right. So I hope you guys are clear. And then do let me know in the comment section anything else you need me to help you with. Again, if you like the video, do help me to subscribe. And then if you'd like to get more videos to help your revisions, press on the notifications bell. Right? Thank you very much. Looking forward to have more revisions on mathematics. Okay, take care everyone. I'll see you guys again.